Newton's second law, the law of acceleration, picks up where the first law left off. According to Newton's first law, an object will keep doing what it was already doing unless an outside force interferes. If an outside force does interfere, it will not keep doing what it was already doing. The object's motion will change. This change we have always referred to as acceleration. Acceleration involves three possible changes. You could speed up, you could slow down, and most importantly, you could change your direction. You could turn. These are the cases we're going to use to describe acceleration. Now, Newton has provided us a tidy little formula for acceleration. Ready? Don't use it. If you think acceleration comes in a three-letter formula, you may make the mistake of associating a force of ma. There is no force of ma, not even this one. Newton's second law is a three-step process. All three steps have to be done in order. Don't skip. If you're working a problem where an outside force does interfere, where there is a non-zero net force, give yourself room for all three steps. The first step is going to look familiar. Step one in dealing with Newton's second law is to make a free body diagram. You did that for Newton's first law. Step two for Newton's second law. No, I'm really not kidding. Make a free body diagram. All right. Once you've made your free body diagram, you're really yanking my chain here. Seriously, make a free body diagram. Do not go on to step two until you've made a free body diagram. You've labeled all the forces with all the formulas you have and all the information you have. Most people skip step two. They're so excited to be done with their free body diagram, they jump straight to the formula. Don't skip step two. Step two is to find the net force in words and letters, no numbers. Write it out and highlight it. Be absolutely clear. If you have numbers but you don't know what they mean, you're not going to get anywhere with your problem. First, mark out what the net force means, what it is relative to the forces you have. The numbers will come in step three. Once you have a free body diagram and an equation with words and letters to go with it, then and only then will you be ready for Newton's second law. Here's the formula you've been waiting for. Acceleration. It's a vector. Check the direction. If it's slowing down or going backwards, is that direction possibly negative? Net force, for which you now have an equation with words and letters, and the mass. Now you're ready to substitute and solve. It's the third step of three, not the first step of one. Substitute your equation in. Now you're ready for some numbers. Solve for anything that needs to be solved. This is the definition of acceleration. It's what acceleration comes from. It comes from a net force working on a certain mass. You'll notice that if you have a very big mass, you'll have a small acceleration. And that's our working definition of mass. Mass, if you remember, is measured in kilograms. If it's in kilograms, it's a mass. If it's not in kilograms, don't put it in the denominator. A small mass is one with a big acceleration. It moves very easily. We say that it's light. It's light because it only takes a small force. Force is measured in newtons to get it moving. If it's in newtons, it goes in the numerator. If it's in kilograms, it does not go in the numerator because kilograms are not a force, they are a mass. Check your units, substitute, and solve. When you're done, you should be getting an acceleration in meters per second squared. Unit analysis says 1 kilogram meter per second squared divided by kilograms crosses out the kilograms and gives us the meters per second squared that we expect for acceleration. This is the same acceleration that's the change in velocity over time. There's your changes in velocity. You could be speeding up, slowing down, and changing direction over time. Let's do an example. The key word in this example is up. See, there we go. It's the house from up. You wish to raise this house up with an acceleration of 2 meters per second squared. Now the mass of a house, 1,500,000 kilograms. And that's a lot of zeros, so let's instead write 1.9 times 10 to the 5th kilograms, 1 power short of a million. How much force would you need to lift this house with an acceleration of 2 meters per second squared? Reaching for your calculator? Don't. Pause the video, do all 3 steps of the 3-step process, press play to check your work. Step 1 in the free body diagram is the label. The whole problem changes based on the label. You're making a free body diagram for the house. Ready? You've got 2 forces on your free body diagram. The force of gravity, aka mg, the weight, and if you want to lift straight up, some sort of lifting force. Who is lifting? Well, in this picture, it's the balloons. This is a very, very complicated realistic problem. First of all, because there are many balloons, therefore we would have many strings instead of one. And second, if you look at the photo from the movie, you'll see that not all the balloon strings are going straight up, and that means trigonometry. We won't get to that till next week. So let's say, in theory, if you wanted to lift the house straight up, what kind of lift force would you want? This is where we get into finding the net force in words and letters, no numbers. The net force from this free body diagram is clearly in the vertical direction. There's F lift going up and the weight, mg, going down. There. Now we've found the net force in words and letters, no numbers, and we're ready to move on to the next line. The acceleration is our net force over the mass, and that gives us F lift, which is our answer, we don't know it, minus m, we have that, g, it's 9.81, all over m. Now we're ready to solve. Solve your equation for F lift, press play to check your work. Cross-multiplying is your friend here, or possibly cross-solving if you know that it's not really multiplying. 2 fractions. 1 here, 1 here. You'll get the non-fraction form of Newton's second law. This is not ma, it's not a force, it's just an algebraic expression. But the net force is F lift minus mg. You can move the mg to the other side easily enough. Now you're ready for some numbers. Now you can say 1.9 times 10 to the 5th kilograms times 2 meters per second, but that's not the only thing in the equation. There's also the fact that in addition to pushing it upward, which is your first instinct, you have to counterbalance gravity. The lift force has 2 parts here. One that balances out the weight, that enables the house not to fall, and another extra boost up here that makes this vector bigger than that one, that makes the lifting force bigger than the weight and enable it to go up, not by 1 count of mass, but by 2. Here we have the weight, and here we have the extra boost. To lift that house upward at a spry acceleration of 2 meters per second squared is going to have to apply a whopping 2.2 million newtons of force. That's a lot of balloons. Next example, let's try the horizontal. You push a calculator with 10 newtons of force. it doesn't pick up speed very much. In fact, it only accelerates at a teeny tiny 0.24 meters per second squared. Was there friction? Well, you saw for yourself. This does not move smoothly. You can even hear it scooching across the page. Of course there's friction. There's a tremendous amount of friction. You're pushing forward. Friction is pulling backward. Pause. Make a free body diagram. Find the net force and find the force of friction. Press play to check your work. Ready? Your free body diagram will have 4 forces on it. Not all free body diagrams have 4 forces. Don't expect everything to look like a T. This didn't have 4 forces on it, but this one has the weight, it has the normal force, it has your push, and it has a force of friction that's a little bit smaller than when you push, but not too much else. Now, we've got the mass. 0.25 kilograms times 9.81 should give you a weight of about 2.45-ish newtons. But we're not ready for the numbers yet. Our next step is to point out that the net force is not in the vertical direction. These are equal. They give you a net force of 0. But in the horizontal direction, we have F push going one way, and the force of friction going the other way. Now, I notice that M times A equals the net force. If it looks reasonable to take that shortcut, you can express Newton's second law this way. Now, we've got numbers. Heavy calculator, but not moving very fast as it picks up speed. Now, the force of friction is the difference between this one and these two. The force of friction is about 9.9 newtons. It's almost in dynamic equilibrium, but not quite. You push, it picks up speed, but not very much. Now, what's going to happen to the calculator if you stop pushing? Watch. No more F push. No more 10 newtons. Just friction. Make a new free body diagram in your notes. Do not muck up your old work. Make a new example for letting go. And make a new free body diagram. Pause, press play to check your work. Ready? What you did here, you do here. There is one force. It is the force of friction. It's pointing backwards. And the net force, that net force is now negative FF. Why negative? It's pointing to the left. It opposes the direction of motion. You may no longer be pushing forward, but the calculator is still moving forward. And as it moves forward, when you let go, it is going to slow down. It slows down very, very quickly. How much does it slow down? Finish your analysis. Solve for A. Pause. Press play to check your work. Ready? It's not accelerating at 0.24 meters per second squared anymore. For one thing, it's got a negative acceleration. It's slowing down. You know the force of friction was 9.9 newtons last time it was moving. Note that negative. You should be getting a much bigger acceleration, and that acceleration should be somewhere pretty close to 40 meters per second squared. Which way? Negative. That there is backwards, that is slowing down, which is why when I stop pushing the calculator, it slowed down almost immediately. Is this even possible? Can anything slow down this quickly? Well, that's why we need to learn a little bit more about forces of friction. You may need to check your number for F push and see if it really was 10 newtons. The formula we'll learn for the force of friction later says if it doesn't look like it's slowing down this quickly, you're probably right.